Is Crummer on her way?
She's finishing up here.
So Taylor, this is Shantz. Shantz, this is Taylor. She referred to you as those people, so there you go. Now you know. Now you know Taylor's name. Don't apologize to me. You should apologize to her.
I miss his crazy suits.
Okay. So the last lesson in chapter 10 deals with composite functions. Remember, your diploma exam is a week from Thursday, 8:30 in the morning. So, unfortunately, we're not going to have a lot of time to review in class. It's just the nature of the course. Losing those couple days in December because it was so cold didn't help. But what I do have is after the notes, there's a bunch of material over there on the side that you can pick up, review material after the notes. There's just one thing missing. I got to send out for it to get photocopied, but everything else is there. So there's 2 booklets for each unit, questions and stuff that you can go through. Okay? So those are there for you to pick up. So we're going to see what a composite function is, write equations of composite functions, and talk about restrictions, as well as sketching the graph of a composite function. So the composition of f at x and g at x is defined as f at g at x. It is formed when g at x is substituted into f at x. So you're working from the inside out, okay? F at g at x means that g is substituted into f. Wherever you see a variable in f, you're going to replace it with all of g. That's how this works. So f at g at x exists only for those x in the domain of g for which g at x is in the domain of f, meaning any non-permissive value won't work. So again, f bracket g bracket x is read as f of g of x, or f at g of x, or f composed with g. Another way to write it is with a little circle there. So it's not a dot that would mean multiplication, it's an actual circle, an open dot if you want. FOG is another way to write f at g at x. Composition of functions must not be confused with multiplications, what I just said. That little circle does not mean f times g at x. Again, it means f OG or f at g of x. So for example, if f at x is the root of x and g at x equals 2x minus 3, then the composition of f at x and g at x is f at g at x, which is the root of 2x minus 3. So again, where does that come from? Well, g is embedded into f. Wherever you see the variable in f, which is just the x under the radical, you're going to replace that with all of g. You're going to embed g into f. So instead of having the root of x, it'll be the root of 2x minus 3. That's where it comes from. Wherever you see the variable in f, you replace it with g. In this case, there's only one term in f. Only one variable, x. We're going to see examples where there's more than one place where that variable occurs. Every place it occurs, you replace it with g. When composing functions, the order is important. F at g at x is not necessarily the same as g at f at x. F at g at x means first substitute g and then substitute the result into f. On the other hand, g at f at x means first substitute into f and then the result into g. So we're going to see a couple of different types that you're going to be working with. In some cases, you're actually going to get a numerical answer. In other cases, it's going to be an expression, just like we had above, an expression, the root of 2x minus 3. For these questions in example 1, though, we're actually going to get a numerical value for all of our answers. Okay, but you work from the inside out. So in this case here, you're first going to find out what g at 3 is. And because you want g at 3, you have to use the g at x function. There are 3 functions listed above, but they're all different. One is f, the other is g, and the third one is h. If you want to find g at 3, you have to use the g at x function and let x equal 3. 3 plus 6 is 9. That's what g at 3 equals. It equals 9. So now we're going to replace this g at 3 with the answer we got being 9. So instead of f at g at 3, it now becomes f at 9, which now we have to use the f at x function to get our answer for that. F at x is 4 times x, and 4 times 9 is 36. So there's the answer. Sometimes you're going to get a numerical answer. Sometimes you're going to get an expression. Question B, again, work from the inside out. The first thing you need to do is figure out what h at negative 2 is. For that, we use the h at x function. H at x equals x squared. All of x is squared, so all of negative 2 must be squared as well. That'll become positive 4. And now we want to find g at 4. Right, we found h at negative 2 to be 4, so we replace that with the number 4. And so now we want to find g at 4, so we have to use the g at x function, which is x plus 6, or in this case 4 plus 6. So there's the value of g at h at negative 2. Question C, we're embedding h into itself, working from the inside out. H at 2, using the h at x function, you square the 2 because h at x is defined by x squared. And so now this 4 gets plugged in for the h at 2. Now we need to find h at 4, which would be 4 squared, or 16. And for the last one, we start by finding f at negative 3. So we have to use the f at x function, which is 4x. X is negative 3. 4 times negative 3 is negative 12. And now we're going to find h at negative 12. So we have to use the h at x function. All of x is squared, so all of negative 12 would be squared, which gives you positive 144. Okay, so in these cases, because we were dealing with a numerical value to start with, our answers work out to be a number. But as we saw in that very first example, and these ones as well, sometimes your expression will involve the variable. So this question says you've got f and g and h. Determine FOG at x. So that is f at g at x. Remember, you always work from the inside out. So in this case, g is embedded into f. So wherever you see the variable in f, which is under the radical, you replace it with g. You replace the x. Wherever you see the variable in f, you replace that with g. And then because f was x minus 1, you replace the x with g, which is x squared, but we still have the minus 1 there. It was part of that function. So what about the domain and range of this function, FOG at x? Well, it's a radical function. You cannot take the root of a negative number. So x squared minus 1 would have to be greater than or equal to 0. That's where we get our restrictions here. And so back in 20-1, and I think we talked about it a few times in this course as well, but you learned about how you determine what values of x will make this true, okay? This is not an equation, it's an inequality. I mean, you can definitely add 1 to both sides, but then you take the square root of both sides to get x by itself. And what does that mean when you're dealing with an inequality? What does it really mean? So instead, what I've always done is I've looked at the graph of the function. The graph of x squared minus 1. So that's a quadratic. It's the graph of y equals x squared shifted down 1 unit. So it's going to start at 0, comma, negative 1, and then it's going to go upwards. We want to know, where is this graph greater than or equal to 0? In other words, where is it above the x-axis? That's where the values of y are positive, greater than or equal to 0. And so what we really need to know is where these x-intercepts are. That's going to determine where the graph crosses the x-axis, where it goes from negative values of y to positive values of y. And for that, we will solve x squared minus 1 equals 0, because we want to find the x-intercepts of this. And the x-intercepts are always where y equals 0. So in this case, we can add 1 to both sides and take the square root of both sides. And when you take the square root and you're solving an equation, remember there's always a plus and a minus. So the x-intercepts are at negative 1, comma 0 and positive 1, comma 0. This is where the values of y change from negative to positive. So our restrictions here are that, and we can write it as our domain, they will go from negative infinity to negative 1, and the negative 1 can be included, because when you let x equal negative 1, you'll get 0 under the radical, and the root of 0 is still 0. But also from positive 1 to positive infinity. This is the domain. It comes from the restrictions. X cannot be between negative 1 and positive 1, because that's where the value of y is negative. The graph is below the x-axis, and you cannot take the square root of a negative number. And so our range then would be that y must be greater than or equal to 0, from 0 up to positive infinity. Now, you can also look at the equation in your calculator. Our equation is the root of x squared minus 1. I'll set my windows to their standard settings. This is the graph of the original function. When we graph the quadratic that's hidden from the calculator, we were just concerned with the radicand, what's under the radical, x squared minus 1. That gave us our restrictions. It led to our domain. But this is the actual graph of the function. And like we said, our domain tells us that it's going to start from negative infinity to negative 1 there, and then from positive 1 to positive infinity. As well, you can see that the graph is completely on or above the x-axis. Y is not negative, and that's why our range is that y is greater than or equal to 0. Okay, so yeah, I mean, you can go into the trace mode and you can let x equal 1, and there's that point there. Y does equal 0. You can let x equal negative 1, and again, that's that x-intercept on the left. Okay, now part B says do GOF at x. G at f at x. So it's the reverse of what we just did. So in this case here, f is going to be embedded into g. So the only place we see the variable in g, because there's only one term there, is that the x is squared. F is embedded into that. The x is replaced with all of f, which is the root of x minus 1. And because in the equation for g at x, because the x was squared, the x minus 1, the root of x minus 1 should also be squared. And in this case, square root and square cancel each other out, and we get y equals x minus 1, which is a line. Now, when we look at that equation, x minus 1, that's a line. It has no restrictions. But we have to look back and see where it came from. It actually came from this expression right there. And for that expression, there are restrictions on x, because you cannot take the root of a negative number. X minus 1 has to be greater than or equal to 0. So therefore, x must be greater than or equal to 1. So again, even though their final expression, our final equation, has no restrictions, you have to look back and see where it came from. Okay? So our domain would go from 1 to positive infinity. And when x equals 1, that is the, when you let x equal 1, y is going to equal 0 in this equation. And so that is the x-intercept. And the graph will go upwards from there. So the range should be from 0 to positive infinity.
Yeah, how about this?
We're good, thank you. Thank you.
Scrambled that message. If you have bottles next week, just set them outside so we're not gonna knock on doors.
Okay. But remember, you can always look on your calculator to see what it looks like. And again, you should use the version that we came up with that I underlined here. It is the root of x minus 1 all squared. So you can see the graph does not cross the x-axis. Even though if you simplify it, you end up with just x minus 1. You have to go back to the original expression to determine your restrictions. So if we go into our trace mode and we let x equal 1, it confirms that that graph starts at the point 1 comma 0 and then goes upwards to the right. Okay? Question C, we have to do 2 composition of functions. F, O, G, O, H at x. So what this means, it means f at g at h at x. And you're working from the inside out. So first we're going to embed h into g. So wherever we see the variable in g, which is the x, we're going to replace it with h. So we're going to replace this x here with h, which is 2x plus 3. And because the x is squared, the 2x plus 3 would be squared as well. So again, starting with g at h at x, the x is replaced with the 2x plus 3, and because the x was squared, the 2x plus 3 would be squared as well. And then we want to find f at this value. So we've already found that g at h at x is 2x plus 3 all squared. So now we're going to take that expression and plug it into the variable in f. And f is the root of x minus 1 So we're going to replace the x there with 2x plus 3 all squared. But it's still a root. And there was a minus 1 after the x. When we look at the expression for f, it's the root of x minus 1. The x is replaced with the 2x plus 3 all squared, but we still have that minus 1 there. So there's our expression. Now you could square the 2x plus 3 if you wanted to. Doesn't really help us in any way, but we definitely could. Okay, we definitely could. And in this one, it doesn't ask us to find the domain and range, but I would probably use the graphing calculator in this case to find out what the restrictions are. So now we'll look at examples where we also graph on a grid. So we've got f and g given. We want to find g at f at x. So that means f is going to be embedded into g. So wherever you see the variable in g, which is this x that has to be squared, you're going to replace that x with f, x plus 1. It's got to be squared, and then we have minus 2. And if you think about or remember when we talked about our transformation stuff, this is a transformation of y equals x squared. It's transformed by an h and a k value. H is negative 1, so the graph will shift 1 left. K is negative 2, so the graph will shift 2 down. Remember, the value of h is always the opposite of what it appears to be, because our general form is x minus h. So if you think about what the graph of y equals x squared looked like, it started at 0, 0. It's going to go 1 to the left and 2 down. That graph also went through the point negative 1, 1. It's going to go 1 to the left and 2 down. It went through the point negative 2, 4. It's going to go 1 to the left and 2 down. It went through the point 1, 1. It goes 1 to the left and 2 down. As well, the point 2, 4. 1 to the left and 2 down. Right, so there's our graph. The domain would be all real numbers. There's no restrictions. Right? There's no radicals or anything here that we need to worry about. Also no denominators. And the range, this graph starts at the point negative 1, negative 2 and goes upwards forever. So it's from negative 2 up to positive infinity. So there's our domain and range. Okay. So we've got two different functions here, f and g. We want to determine f at g at x. So again, working from the inside out, g will be embedded into f. Wherever you see the variable in f, which is this x here, you're going to replace it with g. Because f was under the radical, f at g at x will also be under the radical. And again, this x is replaced with g, 3x plus 1, and then you have the minus 1 on the end. The ones cancel, and you're just left with 3x. And we can look at this as a transformation of y equals root x with a b value of 3, which means it's been horizontally stretched by a factor of a third. Or in this case, we could just do a little table of values. When x is 0, 3 times 0 is 0. and the root of that is still 0. When x is 1/3, and I'm using this point for a reason, 3 times a third is 1, and the square root of 1 is still 1. So the point 1/3 comma 1. Okay. The next point I'll do is when x is 3. 3 times 3 is 9, and the root of 9 is also 3. So that goes through the point 3 comma 3. So that's enough points to sketch a graph. It'll look something like that. The domain and the range are the same. They're both from 0 up to positive infinity. Okay? Number 5, you're given that h at x is f at g at x. This one says determine f at x and g at x. So it's like we're working backwards. So what you need to do here, in some cases is look for a pattern. You see that you have two terms that involve x minus 2. Okay? So again, you got to think about this, that g was embedded into f. Wherever we see the variable in f, we replace it with g. So because we see two terms that involve the x minus 2, I'm going to say that g at x is x minus 2, and it was embedded into f at x, which means wherever we had the variable in f, we replace it with x minus 2. So there was a variable in f that was replaced with x minus 2. It was then squared, plus the x minus 2 is there again, which is another x. And there we have an expression for f at x. And if you take g and sub it into the variable x and f, you'll get exactly what's above there. So you can look back and make sure what we have written down would work, and it does. With question B, there's only one term, one expression, one term under the radical. Okay, so there's a couple different ways that we could do this. One of them would be to say that g at x equals x cubed plus 1, and f at x then would just be the root of x. That would be one way that we could express g and f. I think there's another way we can do it here. We can say that g at x equals x cubed, and f at x equals the root of x plus 1. This would also work. You see, if you take g and embed it into f, wherever you see the variable in f, you replace it with g. That means replacing this x here with x cubed, and you still have the plus 1, which is exactly what h at x is. So there's two different ways you could set this one up. Two different sets that you can have for g and f to get h. There's not really an algebraic approach. It's just more or less looking for a pattern, maybe doing some trial and error, and then checking after to make sure that it works. All right, so for this next one, we have f and g. We want to find g o f at x. In other words, g at f at x. So working from the inside out, f is embedded into g. Okay, f is the root of x minus 1, and it's replaced with or into the x in g. So there's still a negative sign in front of the x in g, and then we'll have the root of x minus 1, and that part will be squared. Notice that g at x is negative x squared. There's no brackets there, meaning only the x is squared, not the negative sign. Now, the square and square root would cancel each other out. So you'll get negative, and then in brackets, x minus 1, which is negative x plus 1. So there's a simplified expression. However, I mean, that's a line with a negative slope, slope of negative 1, y-intercept of plus 1. If we were to graph that, it would go up and down forever, left and right forever. However, when we're talking about restrictions, we have to look at our original expression. Negative root of x minus 1 squared. So let's look at that in our calculator and see what it looks like. So negative, and then we'll have the root of x minus 1, and that's squared. When you graph it, there's restrictions there. This graph will start at x equals 1. If we're going to the trace mode and we let x equal 1, that's where it starts. And the reason for that is if you look at this expression, the x minus 1 has to be greater than or equal to 0. So therefore, x must be greater than or equal to 1. And when we look at the graphing calculator, we see that the graph goes downwards and to the right. So that's going to change our range. Our domain would be from 1 to positive infinity, but our range would be from negative infinity up to 0. Again, the graphing calculator shows us that when you look at that graph. It goes downwards and to the right. Downwards to negative infinity, up as high as 0. So here's another one where we're given h at x and we want to determine f and g. And if we look at this, we can see that there are two places where we have the cube root of x. So I'm going to say that's g at x. And then f at x would be written, wherever we see the cube root of x, we just replace it with x. If you work backwards and you replace all the x's with the cube root of x, you'll get h. Right? So it does check. So once again, we're given f and g. We want to find f at g at x. So g is embedded into f. Wherever we see the variable in f, which is only one spot, we replace that with g. It's still an absolute value function, but the x is replaced with g, x plus 1. So that's f at g at x. But then it also asks us to do f at x. So f is embedded into itself. So wherever we see the variable in f, which is the x, we're going to replace that with all of f. We're going to replace this x with absolute value of x. And so what it means is we're going to have two absolute value symbols. One that was there originally, and the second one comes when we replace the x with the absolute value of x. Now that doesn't change anything at all. You can take the absolute value how many times you want. It's not going to change your answer. But that is the equation. So we're asked to graph each composite function. So the first one for f, that's the graph of y equals the absolute value of x, which remember is a big V shifted 1 to the left. Because here we have an h value of negative 1. Are you with us, Ben? Want to bet a pop on that? You do? That you're with us? Well, you weren't. You were on your phone, so you owe me a pop. You are now, yeah. Good. For how long? Excellent. All right, so this is going to be the graph of y equals the absolute value of x plus 1 shifted 1 to the left. And you can definitely, if you wanted to, set up a little table of values for yourself to make sure that it's going through the proper points. But that's that graph. And then the second one is just the absolute value of x, actually the absolute value of the absolute value of x, but as we said, it doesn't matter how many times you take the absolute value, it's going to end up with the same number every time. Right, so that's that. The domain and the range of these two functions are the same. It'll go from negative infinity to positive infinity, left and right forever. And our range is that y must be greater than or equal to 0. Okay? Looking at example 5, a spherical weather balloon is being inflated. The balloon's radius r in feet after t minutes is given by r equals the root of t. Express the volume of the balloon as a function of time t. So to do that, you need to know what the formula for volume of a sphere is. And if you were asked to do a question like this on a test, you'd be given the formula for volume. That's the formula for volume. But that is in terms of r, the radius. We're asked to write this equation in terms of t. And we can do that because we know that r equals the root of t. We're told that above. So if we make that replacement, now we'll have v equals 4/3 pi times the root of t cubed. And you can write it like that, or you can write it as 4/3 pi times t to the 3/2. Denominator tells you what the root is. It was a square root, so that's why the denominator is 2. And it's raised to the power 3, so that's the numerator. So there's part A done. Now part B. After how many minutes will the volume be 4,000 cubic feet? So volume is 4,000. We need to solve for t. So we can start by dividing both sides by the 4/3. So 4,000 divided by, in brackets, 4/3. That gives us 3,000 equals pi times t to the 3/2. Then we would divide both sides by pi. (954.9) will equal t to the power 3/2. And to get what t is, we need to get rid of the power 3/2. We can do that by raising both sides to the reciprocal of 3/2, which is 2/3. On the right, you'd multiply those exponents together. That's what you do when you have one exponent raised to another, and you're going to get t to the 6 on 6, or t to the 1, or just t. And so we have to find out what 954.9 to the power 2/3 is, which, I mean, you can just do that on your calculator. I have that number in there. I can go to the power of 2/3. Calculator will do it. That means the cube root of 954.9 squared. You could do it that way as well. But there's our answer. And so it'll be approximately 97 minutes. Approximately. And the only difference between that one and this next one is now we're talking about surface area. The balloon's radius r in feet after t minutes have elapsed is given by the same equation, but now we want to express the surface area of the sphere. And the surface area of a sphere is 4 pi r squared. Again, you'd be given this if you needed it. But we're asked to write this in terms of t instead of r. But once again, we know that r equals the root of t. So we can make that replacement. It'll be 4 times pi times r, which is the root of t that needs to be squared. And in this case, square root and square cancel, and you just get 4 pi t. So there's part A. For part B, after how many minutes will be the surface area be 180 square feet? So 180 will equal 4 pi t. And now it's just a matter of dividing both sides by 4 pi. And when you do this in your calculator, you have to put the 4 pi in brackets if you're going to do it all in one step. So that it's 180 is divided by 4 and divided by pi. Without the brackets, your calculator would divide 180 by 4, and then it would multiply that answer by pi. You get an answer that's over 6 times bigger than it should be. So approximately 14.3 minutes. Or seconds, I should say. Nope, minutes. Okay? So you could work on page 507, questions 1 through 4 and 6. I will post those solutions to Google Classroom. So again, tomorrow we'll start chapter 10. We're not going to have any quizzes in this unit because we don't really have the time. So tomorrow we'll start chapter 11, and then that'll be it. So again, there are, I think, 5 different stacks there. 7. So you can pick up one of each, and I'll send out the other ones right now so that we have them for tomorrow. So you guys can start reviewing for the diploma exam.